We have talked about summing moments to get resultant moments. In this video, we're going to sum moments to perhaps answer a different question. So in this problem, 4-6, we're going to compare the moments and see which one is greater. So what's happening is the person is pulling down on this crowbar and trying to pull the nail out of the wood. The nail is stuck in the wood with a force that takes 155 pounds to pull it out. And the person's pulling down with a force of 25 pounds, and we're going to see if that's enough to pull out the nail. So first of all, understand that the point of rotation is the contact point right there. That's where we will sum the moments about. So let's look at the nail first. How much force does it take to pull the nail out? We've determined that, 155 pounds. And what's the moment about point A that can allow us to do that? Well, if we look, I'm going to zoom in here and get a little bit closer on the picture, and let's put the components of the force right there. So this is going to be a component this direction and a component in this direction. This one will be 155 cos 60, which makes that 155 sine of 60. So if we look at the moment about point A required to pull that out, it would be 155 sine 60 times that 3 inches. So let's look at that. And there's the the calculation for the nail. The moment about point A necessary to pull the nail out would be 155. Well, in this case I put cos 30, which also works. Let me just put that in there. If that is 30, if that's 60 degrees up there, then that'll be 30 degrees there. So cos 60 and sine 30 are going to be the same thing. Same thing of 155 sine 60 would be the same as 155 cos 30. Regardless, it takes 403 inch-pounds to pull that nail out. Now let's look at the bar. The bar also rotates about point A, and we have kind of a interesting trigonometry problem here because it's a little bit offset. So there's two ways to look at this. If I have this force pulling down here, and if I knew what the perpendicular distance is, I could figure that out. So let's zoom in here and see if I can find those two components of the perpendicular distance. There's going to be this part here, and this looks like this is going to be 20 degrees, because that's going to be 20 degrees. So I can see that this is going to be 14 cos 20 for that portion of it. Now how about this piece right in here? If I look at this, if that is 20 degrees here, that angle right in there is also 20 degrees, which makes this distance right here 1.5 sine of 20. So you may have to do a little bit of trig on your own to convince yourself that that's the distance. But if I could do all that, then I can see that the moment about point A is 25 times, let's go ahead and zoom out just a little bit, 1.5 or 14 cos 20 plus 1.5 sine 20, and it is equal to 342. The other way to look at this is to look at force P and break it up into its two components using Varignon. So let me again zoom in. And I have two components, or two possible ways of looking at this. There would be a force component of P there. Let's go like that. And a component going this way. And again, if this is 20 here, then this is going to be 20 right in here. So this is going to be P cos 20, and this one will be P sine 20. P cos 20 will have this lever arm, which should be just 14. I know this is getting a little bit muddy, but I hope that you'll be able to see that. And the P sine will have this lever arm, which should be 1.5. So it actually is about the same amount of work to try to find out what that total distance is. But let's go ahead and zoom out and look at the calculation. And so I have 25, which is P cos 20 times 14, plus 25 sine 20 times 1.5, and I get the same answer, 342. Okay, so in this case we did get the same answer, which is handy, and you can see that the value that is generated by the bar is 342 in both cases, which is insufficient to pull out the nail. In other words, I needed at least 403 inch-pounds to pull the nail out, and I'm only generating 342, so I can't quite pull the nail out. In this wheelbarrow problem, we're looking for the weight that is balanced by the force that is applied here. What we're going to look for is, let's just draw the weight coming down. The weight coming down comes from the center of gravity of the wheelbarrow. So that's coming down at some weight or some mass, and we're saying that the force here is equal to 100 newtons, and we want to find out what is balancing that force. So let's look at the components of the force. First of all, we know that let me zoom in a little bit. I know that there's a component in this direction and a component in this direction. So this will be 100 cos 30, and this one will be 100 sine 30. And those two components have the following lever arms. If I say that the point of rotation is point A, then 100 cos 30 has this lever arm, and 100 sine 30 has this lever arm. So let's go ahead and add those in there, or we'll put those into the calculation. So the moment about point A, let me zoom out just a little bit. The moment about point A caused by that force is 100 cos 30 times this lever arm plus 100 sine 30 times this lever arm, and it's balanced by the force going in this direction times this lever arm. But we don't know that force, we just know that it is the weight, which is mg, times 0.3. Now let's look at the signs, SIGNs here, and just make sure we're doing this correctly. Both of these forces are causing rotation in this direction, which is positive counterclockwise. The weight coming down this way is trying to rotate in this direction, which is negative, so that would be clockwise moment, so that's why the negative sign there is. And if we want to have a balance, that means the moment is equal to 0, so all we have to do is solve for the weight here. The mg is equal to the weight, that's equal to 581.9 newtons. Solving that for the mass, we get 59.3 kilograms. So this next problem, I'd like you to pause the video and see if you can solve this on your own, and then we'll go through the solution a little bit. But what we're looking for is how to balance all of these masses on this crane. So we got a crane, it's kind of way up in the air, it's got a mass here, it has this lever arm, and a mass here which has this lever arm. The weight of this portion of the crane has a center of gravity here with this lever arm, and the mass of the load has this lever arm. And what we're trying to do is find the mass of the counterweight of G3. So in other words, this is my unknown. So go ahead and work on that and see what you can get. So this is a fairly straightforward problem, but what we're looking for is the mass of G3. So let's go ahead and put the weights in here, put the weights drawn down as like we would put in a free body diagram, which we're not quite there yet, but we're going to draw those forces coming down, and they all are in the vertical orientation, so it's pretty easy to see that the perpendicular distances that we're looking for are given in the picture. So some of the moments about A. We have mg3, which is this one, times this lever arm. That's going to be my unknown, 7.5. mg2 times this lever arm, which is right there. Those are both going to be in the positive direction. Those are counterclockwise. mg3 or mg1, which is going in this direction, is listed right there, and the weight is going in that direction, which is also negative. Anyway, put all the numbers that we know in, and we can solve for the mass of the third counterweight, and you can see that it's 4967.